Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to discuss independent random variables. When we discuss many random variables, sometimes some random variable they may have a relations within themselves or sometimes may not. So, it is important to study whether these random variables are having some dependency or not. So, this dependency can be studied by using a nice mathematical way through the CDF, that is a joint CDF. If the joint CDF of a two-dimensional random variable or n-dimensional random variable satisfies some conditions, then we can conclude those random variables are independent. Then the next question comes, why do you need to study the independent of random variables? If the random variables are independent, then some of the prediction or some of finding the probabilities of those random variables will be easy when those random variables are independent. So, let me start with the concept called independent random variables. Let me start with the definition of independent random variables, then a few more properties when these random variables are independent. At the end, I will give one or two examples for the conceptual understanding. The definition. Let me start with the two-dimensional random variable, then the same concept can be extended to the n-dimensional random variable. So, that way it is easy to explain the concept. We say that the random variable x and the random variable y are independent if and only if the CDF of a two-dimensional random variable that is same as the CDF of a one-dimensional random variable with the product. Whenever I write the suffix, that means the CDF is corresponding to that random variables. So, f suffix x comma y, that means it is the CDF of two-dimensional random variable. F suffix x, that means it is a CDF of the random variable x. F suffix capital Y, that means the CDF of the random variable y. If the product of CDFs of the random variable x and y, that is same as the CDF of two-dimensional random variable x comma y for all x comma y in R2. Then we can conclude this is a independent random variables. This is a if and only if condition. That means if two random variables are independent, this condition will be satisfied. If this condition is satisfied, then we can conclude both the random variables are independent. It is immaterial of the random variables are of the discrete type or continuous type or mixed type, because the CDF is always exist whatever be the type of random variable. Here we are saying the two random variables are independent if and only if the condition on the CDFs. That means if I have for any pair of Borel sets. Suppose I keep the Borel set A and another Borel set B of a real line. Then we have, if two random variables are independent, then the probability of x belonging to the Borel set A and y belonging to the Borel set B, that is same as the probability of x belonging to the Borel set A multiplied by the probability of y belonging to Borel set B. That means if two random variables are independent, the if and only if condition is satisfied. Whenever two random variables are independent, then we can always get the probability of x belonging to Borel set and y belonging to another Borel set, that is same as x belonging to the one Borel set multiplied by probability of y belonging to the other Borel set. This is if this condition is satisfied, then x and y are said to be independent. Whereas the first condition is the if and only if condition. We are not saying the random variable is a discrete type or continuous type. Now I am going to make a condition on whether the random variables are of the discrete type or continuous type and how this if and only if condition changes. That is a necessary and sufficient condition for the random variables x and y of the discrete type to be independent is the joint probability mass function of x and y, that is same as the product of the probability mass function of x with the probability mass function of y. This is for all pairs xi, yg. That means this is a if and only if condition. If both the random variables are of the discrete type, then the independent condition on the CDF can be replaced by the independent condition on the joint probability mass function. Our joint probability mass function is same as product of probability mass functions of x and y. This is also if and only if condition. That means if two random variables are of the discrete type or independent, then this condition will be satisfied. We call this condition as a independent condition. Similarly, if this condition is satisfied for all pairs, then both the random variables are of the discrete type and they are independent. The similar results is for the continuous type also. Two random variables x and y of the continuous type are independent if and only if and only if you have to replace the condition of the CDF by the probability density function. So, the joint probability density function, when I write suffix x comma y, that means it is a joint probability density function of x comma y. that is same as the probability density function of x multiplied by probability density function of y. This is for all x comma y. So, if this condition is satisfied, then two random variables are of the continuous type or independent. If two random variables are of the continuous type or independent, then this condition will be satisfied for all x comma y. Therefore, the condition for independent random variables either in the level of CDF, or if it is a discrete random variable in the form of probability mass function. If the random variables are of the continuous type, then it is a probability density function form. So, all three are going to be if and only if condition, not the only one side, it is in the both side. So, even though we have explained through the only two dimensional random variable, this can be extended to the multidimensional random variable also. That means let x1 comma x2 comma so on be a n dimensional random variables with the CDF capital F is a function of n variables. We say that the random variable x1, x2, xn are mutually independent random variables if and only if you take any fewer random variables CDF k for k is equal to 2, 3 and so on till n, that is same as product of I is equal to 1 to k, the CDF of those random variables CDF. This means if you take any two random variables, the CDF of those two random variable is same as a product of CDF of only those two random variables. If I take any 5 random variables when n is greater than 5, then CDF of 5 random variables is same as product of those 5 random variables CDF. Then we conclude they are mutually independent. It is same as the mutually independent events. If you have n events and once you say that they are pairwise independent, that means any two events satisfies the independent concept or independent condition, then they are called pairwise. If it means mutually, if they are mutually independent, that means whatever be the collection of events you take, the independent condition is satisfied, then we conclude they are mutually independent events. The same thing here, if you have n random variables, whatever be the number of random variable you take it from those n random variable that satisfies the independent condition, then it starts from any two till all the random variable, then we conclude they are mutually independent. Whenever we say more than two random variables are independent, that means by default they are mutually independent. Many times we won't write again and again mutually independent word when we discuss more than two random variables, but whenever we have more than two random variables, when we use the word independent random variable, that means they are mutually independent. That means the independent condition is satisfied for all the forms of collection of random variable satisfying the independent condition. Now we will move into some problem of explaining how the independent random variable is playing a role. The first example, that is same as the example which we have considered earlier. That is, let x comma y be a continuous type random variable, two dimensional, continuous type random variable with the joint probability density function is of the form f of x comma y, that is after we find the value of k, we got 24 x square divided by y cube when x is lies between 0 to 1 and y is greater than 2, otherwise it is 0. So, this problem just now we have discussed when two random variables are of the continuous type. For that we found the k, that k value was 24, and we found the probability of x between some interval. Here we will verify whether these two random variables are independent or not. So, this is a joint probability density function. Already in the same example we got the probability density function of x, that is 3 times x square when x is lies between 0 to 1, otherwise 0. Similarly, we got the probability density function of y, that is 8 divided by y cube when y is greater than 2, 0 otherwise. Easily it can be verified. In this example, the joint probability density function is same as the product of probability density function of random variables x comma y, because it is 3 times x square, the other one is 8 divided by y cube. Not only that, the 3x square is a range between 0 to 1, and 8 divided by y cube, the range is y is greater than 2, which is same as if you make a product, that is 24 x square divided by y cube, and the range of x is 0 to 1 and the range of y is 2 to infinity. That is same as the joint probability density function of 24 x square divided by y cube when x lies between 0 to 1 and y is greater than 2. So, the interval matches and the value matches, 0 otherwise matches. Therefore, for all x comma y, the joint probability density function is same as the product of probability density functions of x and y. Therefore, these two random variables are independent. Therefore, x and y are independent random variables. Each one is of the continuous type. We can check it from the CDF also, that is if and only if condition for the CDF, but since the joint probability density function is given, you can find the probability density function of x and y, then you can verify the independent conditions on probability density function, that is satisfied. Therefore, both the random variables are independent. We will go for one more example, example 2. Again we have a continuous type. Let x and y be random variables of a continuous type with the joint probability density function, that is f of x comma y, which takes the value 6 when x is lies between 0 to 1 and y is lies between 0 to 1, as well as 3y is lesser than x, less than or equal to x. So the joint probability density function is greater than 0, that is 6 when x is lies between 0 to 1, y is lies between 0 to 1, and 3y is less than or equal to x, 0 otherwise. Before we proceed the problem, we can always verify whether this is a correct joint probability density function. That means if you integrate double integration over x and y, this has to be 1. So one can verify this is going to be double integration is 1, therefore this is a correct joint probability density function. From this one can find the marginal distribution of x by integrating the joint probability density function with respect to y. If you do the little simplification, you can get the answer, that is 2 times x when x is lies between 0 to 1, otherwise it is 0. You can verify this result also, whether this is a correct probability density function of x by integrating 0 to 1 2x, you will get the value 1 and it is greater than or equal to 0, therefore this is a probability density function of x. Similarly, you can compute the probability density function of y by integrating the joint probability density function with respect to x. Here also I am skipping the integration part. One can get the answer, that is 6 times 1 minus 3y when y is lies between 0 to 1/3, 0 otherwise. That means within this interval 0 to 1/3 the probability density function is greater than 0, 6 times 1 minus 3y, otherwise it is 0. By seeing the probability density function of x and the probability density function of y, this product is not going to be the joint. That means the f of x comma y is not equal to the product of probability density function of x and y. For all x comma y, if this condition is satisfied equal to, then you can conclude they are independent. But since by seeing this you can say it's 2 times x, 6 times 1 minus 3y, whereas the joint probability density function is 6. Obviously you can say they are not equal, therefore x and y are not independent random variables. So I have given the first example in which they are independent random variable by finding the marginal distribution, whereas in this example by finding the marginal distribution of x and y, we are concluding condition is not satisfied, independent condition is not satisfied, therefore they are not independent random variable. We will go to the one more example, that is example 3, because already we discussed 2 problems of the continuous type. We will see one problem of the discrete type also, that is let x and y be a discrete type, let x and y be discrete type random variables with joint probability mass function is given by, if you recall, this is same as the problem which we have discussed in the last class. The possible values of x is 0, 1, 2, 3 and the possible values of y is 1 and 3, where x denotes number of heads obtained when we tossing a unbiased coin 3 times, and y is the difference in absolute of a number of heads and a number of tails obtained. Therefore, the possible values of y is 1 and 3, and the possible values of x is 0, 1, 2 and 3. And in that problem we have got the joint probability mass function, that is 0, 3 by 8, 3 by 8, 0, then 1 by 8, 0, 0 and 1 by 8. And in that problem we have got the marginal distribution of x and y also, if you recall. So, for possible values of x, that is 0, 1, 2 and 3, and the probability of x takes the value x, that is going to be 1 by 8, 3 by 8, again 3 by 8 and 1 by 8. So, this is a probability mass function of x, and similarly the probability mass function of y, that is 1 and 3. So, 1 it takes a value 6 by 8 and 3 it takes a value 2 by 8. So, this is the probability mass function of y. Now, you can verify whether these two random variables are independent. Suppose x takes a value 1, y takes a value 1, that probability is 3 by 8. Here x takes a value 1 and y takes a value 1, that is this much. So, if you make a product of 3 by 8 into 6 by 8, that is not equal to 3 by 8. Even at one pair it does not satisfy, then you cannot conclude it is independent random variable. If all the pairs, the joint probability mass function is same as product of probability mass functions of x and y, then only you can conclude they are independent. Since any one pair does not satisfy, then you can immediately conclude both the random variables are not independent. This will be a sort of obvious because the random variable y is defined as difference in absolute with the number of heads and number of tails, whereas the random variable x is defined number of heads. That means the y itself is a function of x. That means y is dependent on x. Therefore, there is a dependency between the random variable y and x in the definition itself. Therefore, from there itself we can conclude they are not a independent random variable, but that we have concluded from the distributions also.